Now I want to teach you something that at first glance looks like it'd be very, very complicated. In fact, it's often taught like it's complicated, but actually it's very straightforward and very actually quite easy to do, and something you can actually with a little practice you can actually do this in your head. And what I'm talking about doing gap calcs. In other words, uh, calculating the gap between two fields if you want to match at a certain depth in the patient. So the situation would be like this. We've got our patient like this, and we have, say, one beam coming in like this on the patient, and then another beam coming in like this. And if we match right on the surface, we'd get an overlap, all the way down into the patient. So the idea is usually you pick a certain depth where you want that overlap to happen. So we're going to accept some overlap down here, but we don't want it above this. And so usually this point might be the spine. That's the most common one. You don't want to have any overlap on the spinal cord. So and then what you're going to do at, say, at a certain depth, say that was the depth of the spinal cord, you're going to figure out what would be the gap on the surface between these two fields, so that you're not overlapping on the spine. And I can draw it in here. So say the spine is like right along in here, and that's where we don't want to have overlap. So that's the depth we pick that we're going to calculate this gap on. So now this, if you just look at that, looks like that'd be a little bit complicated, but it's actually just a straightforward geometry problem. All right, so let's just do the first part. We're going to divide this problem into two parts. The first part is that we're going to, let's see, here's the back of our patient. We've got a beam coming in like this, and this beam is at 100 centimeters SSD, and it is a 40 centimeter wide field, and this is symmetric. So this is the beam coming in here, 100 centimeters SSD. It's 40 centimeters wide, and this is our depth that we're going to match to, and this is our little this is one half of the gap, which is we're going to call G1, or just I shouldn't say one half, but this is part of the gap that we're going to calculate. So right now we're just going to calculate the contribution to the gap from this first beam. How big, and then of course the second beam will be coming in over on this side. We're going to do that next. So how are we going to do? So we got some numbers now: 100 SSD and a 40 centimeter wide field, and we want to. And let's give you a depth for D. Let's say that's it's typically right around 6 centimeters. So let's say D is equal to 6 cm, and that's what we're going to. So we're now going to calculate this G1 here. All right, the first thing I'm going to do is bring you back to the days of high school geometry. And let's look at this not in terms of radiation beams, but just as triangles. And we're going to look specifically at this triangle here and this triangle here. The first thing to notice is that since this is coming straight down, that this angle here is a right angle. That's 90 degrees, as is this one, because we're going straight down. So here and here we have two 90-degree angles. And also, because these are two cross lines, this angle here and this angle here, these inside angles, are the same. We don't have to figure out what they are, but those just that you see that this angle and this angle are the same. Anytime you have, two lines that cross, if these are straight lines, mine aren't too straight, but this angle and this angle are the same, as well as this angle and that angle. Anyway, so that's just something from high school geometry. Hopefully you remember. And we can also say that if we look at this angle up at the top right here, then because we have two angles in a triangle that are the same, this angle and this angle have to be equal as well. And that just comes from the fact that triangles always add up to 180 degrees. So if you already know two of the angles, like we do here, that third angle and this angle have to be the same. In other words, this big triangle right here and this little triangle here are similar triangles. That just means that they are in proportion to each other. So if we compare the ratio of similar sides, that's going to be the same between each triangle. So specifically, let me write this out here. The first thing I want to point out is that this side here of this triangle is 20 centimeters. The way I got that is just I said that this was a symmetric opening. It's 40 centimeters. Half of that is 20. Hopefully you see that. So that side of the triangle is 20 centimeters. Now I can say that just looking at these triangles, this one is just an upside down version and backwards version of this one. Do you see that here's your right angle here, here's your right angle here, that G1 should be to this depth D, which we said is 6, but G1 is to D as 20 is to 100. This side is 20, this side is 100, this side is G1, that side is D. So I can write this out as G1, this gap, divided by the depth is equal to 20 divided by 100, this side of the triangle here. And since I know that D is equal to 6, all right, I can rewrite this as G1 is equal to 20 centimeters divided by 100 times 6. So I just took, anyways, I said this D is equal to 6, multiplied it through, and that's going to equal 1.2 cm, which I can prove to you here. We had 20 divided by 100 times 6 equals 1.2. All right, so that gives us this gap, that part of the gap we're going to want on the surface will be 1.2 cm. All right, now let's do the second part of this problem. So I'm going to, again, this is the other beam. Let's say that this one is also at 100 centimeters SSD, but this one we're going to say is 20 centimeters wide. It's symmetric, but it's 20 centimeters instead of 40. And the depth, we have our depth at 6. And now we're going to calculate this little part here, G2, the part of the gap that is due to this beam, the gap on the surface. And let's say, so right here, this half of this triangle, we have our similar triangles right here now, here and here. This part of the triangle is 10 centimeters. Now we have 100 centimeters SSD down to here. And then here's our triangle right here with, we could say that G2 is to D as 10 is to 100. Let's put that down here. So G2 is to D, this part of the triangle is to D as 10 is to 100. Again, it's just similar triangles. Nothing to do with radiation, just a simple geometry problem. So hopefully you see that. All right, and so if we write that out, I just brought this D up over on the other side. The D is 6 centimeters. So the G2, this gap 2, is equal to 10 divided by 100 times 6. That's going to be 0.6 cm, which I'll prove to you with my calculator. So again, we have 10 divided by 100 times 6, 0.6 centimeters. So this little part of the gap is 0.6 centimeters. Now what happens when we put them all together? All right, putting these together, we've got our two beams here, and we want to match at a certain depth, 6 centimeters in this case. And we've got our two beams. We said that this was, these are each at 100 SSD. This beam is 40 centimeters wide. This one was 20 centimeters wide. And we're going to we calculate our two gaps, which were right here. So this was the first part of the gap was right here. This was G1, and the second part was right here, and this is G2. And we said that G1 was equal to 1.2 cm, and G2 was equal to 0.6 cm. So 1.2 plus 0.6 is equal to 1.8 cm. That is the amount. That is the gap on the surface between the edges of these two beams that we would need in order to match at a depth of 6 centimeters. I think I'm going to go on, teach you some more complicated ways, but I'm going to stop here to make the one lecture out of this one, just so if anything here is confusing, I would suggest you go back, watch it again, make sure you understand about the similar triangles, because now I'm going to make it a little bit more challenging, but I want you to make sure you understand this part first. So I'll break these up into separate lectures.